So I guess I'll get started. So yeah, last time was sort of just the intro lecture where we talked about what the class is going to be about and the syllabus and everything. And then today and Thursday are going to be really introducing a bunch of the terminology that we're going to be using through the rest of the course and the main algorithm that we're going to be using. But today really is about, hey, here's a bunch of definitions. Here's what we're going to be doing. We're going to be using these for the rest of the course. So today's lecture is a bit dense. Not all of them will be like that, but just got to cram it into one lecture, and then you'll have it as a reference for the slides. And a couple of people asked me about JavaScript, like how to set up all of that. So the assignment where we talk about, or sorry, the lecture on Tuesday in a week from now, when we talk about assignment 1, I'll show you the whole setup process. There's actually no setup process, but I'll show you what I do to get things up and running. And so if you had any questions about like the setup of the assignments or anything, that'll all be answered in the first lecture. And you don't need to worry about it till then because you don't have the assignment anyway, so you can't really work on it. But a couple of people said that they're not very familiar with JavaScript. I wouldn't worry about that too much. The features of JavaScript specifically that we're going to be using, like I said before, just like for loops, arrays, basic classes and stuff. And so if you want to go out and do a little bit of JavaScript and like refamiliarize yourself with it or do a couple of tutorials, that's fine, but you should be fine just with the lecture material itself. Some of you saw over the weekend I posted on D2L, there's a survey here. It's a completely anonymous survey. I just wanted to get your feedback on the lecture videos and what you think and stuff. So only a few people have filled it out so far, but just to show you, it'll just take like less than a minute to do it if you can just go on D2L and do that whenever you have a chance. So okay, now that that there's going to be lecture recordings, like how many of you plan to come to class? That's like completely up to you if you come to class or not. I'd just like to know. How would you prefer to watch the lecture videos? So most people so far have said they're probably going to watch them on YouTube. How important are the lecture videos to you? What is your opinion on them being posted to YouTube? How was the quality so far? Medium to high quality. That's basically all I can hope for. If I'm not in control of the recording, I have to work with what they use. And it takes me a minute or two to put that cropping of me up in the corner of the video. So did you really care about that? I think most people said it's fine, so maybe I'll just keep doing that. And yeah, it's completely anonymous. You can see that I can't see who answers it. It's just sort of a summary view. So please go fill that out if you can. So lecture number 2, agents, actions, and environments. This is what it's all about. And I mentioned this a little bit before, but this is probably the most dense lecture of the course in terms of how much terminology there is. It's fine, you don't have to remember it all right now, but in terms of like the single lecture that's probably most important for the midterm, there's going to be a few questions about the stuff that we learned in this lecture on the midterm, but we'll be revisiting this stuff as we go. It's stuff that we'll be using the whole time. So it's not like this lecture is the midterm, but there's a lot of stuff to remember in this one. And just remember that I am going to post the PDF slides, so you don't need to spend the whole time writing notes. And don't worry if you don't get it all today, because we'll be talking about this stuff the whole course. And things will be reiterated in later slides. And of course, use the slides as a reference for your assignments, for study materials, for whatever. So what is an agent? Well, an agent exists in a specific environment. So I am an agent in the real world. Super Mario would be an agent in Super Mario World. A robot would be an agent either in the real world or in a simulation, right? There's an agent doing something that we're interested in. And so the agent is the entity for which we want to make decisions and take actions. So for example, if I had a robot in this room, there would be other things moving around making decisions, like maybe you're all here as well. But for the decision-making AI problem that we're trying to solve, there's usually one or more agents that we've specified as the agent that we want to make decisions. So in that case, it might be the robot who's maybe trying to deliver some coffee or something like that. In most cases, the environment defines the problem, and the agent gives a solution to that problem. And we'll talk about that in a little bit. And there are many, many types of agents. So one type of agent is a Roomba. Does anyone actually have a Roomba? I don't. We have pets, and I'm kind of scared what it might do to the pets. But yeah, a Roomba, its task is to clean the floor, right? It's a little vacuum, goes around in whatever pattern. And so if you were given the task of, okay, make this agent keep the entire apartment pretty clean, how would you solve that problem, right? That's a problem that we'll be looking at. Not exactly cleaning a floor, but how to most efficiently navigate around. Here's a bit more of a complex agent. So this is Spot from Boston Dynamics. It's a robotic dog that can jump really high and run really fast and perform some basic motor skills like opening packages or like sniffing out bombs or whatever. So the Spot here would be the agent in whatever problem it's trying to solve. Here's a problem called the pole cart problem. And so this is an agent that can just move left and right. That's all it can do. And you can think of this as like if I had a meter stick or something, I'm trying to balance something on my hand, right? So if I'm in 2 dimensions, I'm trying to balance it by just moving it left and right. And so the problem here might be give actions of moving left and right so that this pole stays balanced the longest, right? So that's another example. Another example might be a player in a game, right? So depending on the game, the agent is going to be different. So in the game of chess, individual pieces are not individual agents, right? Because we're not really concerned about, hey, what can a rook do? Or what can a knight do? It's the player that would be considered the agent or the decision-making function in that system. So here the agent would be the player in a game of chess. And as I said before, the agent really depends on the problem, right? So what's the agent here? Is it Mega Man? Is it the dragon chasing Mega Man? Well, it depends completely on the problem that you're trying to solve. Did you have a question?
Yes, even as like in chess, is one player an environment to the other player, or both of them are agents?
So we'll talk about that. I'll get to that specific. Okay. It depends on the number of players and like the type of problem you're trying to solve. So it completely depends on the problem. But I'll give examples of that in a bit. In fact, chess is one of the best examples, so we'll be talking about chess quite a bit. So an agent within an environment takes actions to achieve a particular goal. So ideally, we are going to be giving our agent some sort of goal, whether it's solve the maze the fastest, or beat the other person at chess, or get the most points, and then it will try and take actions to achieve that goal. The agent is going to perceive its environment somehow and make decisions about which action to take. So if I am a human agent, I have however many senses that I have, sight, 5 main senses at least. I can see all of you, I can hear some of you, and I can walk around, stuff like that. So I can perceive my environment somehow. And we'll talk later about how there are certain parts of my environment that I can see, but like I can't see under your desks. Right? So there's certain parts of it that I can't see. And then I'm going to make a decision about which action to take based on the knowledge that I have. The agent is then going to take that knowledge, make a decision, take an action, and then that action is going to change something about the environment, right? Something may change. Usually something does change, even if it's just the position of the agent. But something is probably going to change, and then that whole process repeats, right? So this will be kind of a loop. And so artificial intelligence, one way of looking at it, is the algorithmic discipline of making these decisions for these actions more intelligent, right? So how do we solve the goal within whatever optimization criteria that we want to? And so what we have here is we're going to have an agent. In some cases, maybe we have multiple agents, but we have an agent and we have an environment. The agent is going to take actions. Those actions are going to affect the environment somehow. So if I move a chess piece, well, the chess piece has been moved. Maybe I take a piece off the board. And then the agent, after seeing the new state of the environment, is going to observe some of that environment, maybe the whole environment, and then this cycle repeats. And the cycle will repeat. If I'm a human, well, it'll repeat until I die. Or if I'm a robot, maybe until the battery wears out, or until the game is over, or until whatever happens. So agents, as I said, they perceive its environment through sensors. So some examples of that, if I have a robot, maybe the robot has a camera, or a laser rangefinder, or sonar. Humans would have their 5 senses that they can detect things in the room. In games, might be a little bit different. We maybe have like keyboard input or controller input. We have the RAM, like the internal state, or the entire game state, right? So if we're making a chess playing algorithm, we probably don't need to have like an actual chessboard with a camera and a robotic arm, right? We would just program the game, and then the agent could read directly from RAM. Like it could just read the game state without having to have any camera or laser or anything like that. So when we use games, most of the time, we're talking about just reading the game state directly from RAM. And then it acts on the environment through what are called actuators. So for robots, they could be wheels, tracks, arms, whatever can actually physically interact with the world. Humans, we might have limbs, tools. I have this laser here that I'm shining. And for games, we would have some predefined rules or actions like, the knight on a chessboard can move 2 over and 1 up, or vice versa. The queen can move in any direction, etc. So we'd have some predefined rules for that. And agents may also, they may have some knowledge of the environment. Like if I had to go from here to, I don't know, the engineering building, I have a lot of knowledge about that problem. Like I kind of know all the obstacles that are in the way. But if you put me like in an unknown city somewhere and said, hey, go to the nearest police department, I may not have any knowledge of that. Now, I would have some knowledge, like there were probably roads, there are cars on the road. I could use that to my advantage somehow. But the agent may have some knowledge, it may not have any knowledge at all, right? So a percept of an agent is the agent's perceptual inputs at any instant. And so it's kind of the agent's current belief of the world, and we call this the environment's current state. So think of, if your only input is visual, if you have a camera, then a percept would be a still photo, right? Here's the state of the environment at that time. Or it's one state of the game of chess or StarCraft. It's like an instantaneous knowing of what's going on. And again, that may be the whole state. Like in a game of chess, we'd know where all the pieces were, all the pieces that are missing. But if I'm looking at like the state of this campus, there's lots of stuff that I can't see on campus. And so if that's a percept, then a percept sequence is the complete history of everything that the agent has perceived so far, right? So taking everything that I've seen since the start of this problem, that is the sequence of percepts. So you might call that like the history so far in the problem. So in general, an agent's choice of action at any given time, that can depend on the entire percept sequence up until now, right? So for general problems, like especially in the real world, the hardest type of problems, you can't just look at what's happening this instant. You have to have known what's happened in the past as well. And so in this course, we're only going to look at problems where the current state is sufficient to decide on the optimal action to do. And we'll talk about that a lot more in the future and give like really specific definitions for that. But for now, we are looking at fully observable states for the problems in our assignments and the problems in the course. It means a game like chess, for example, where I can see everything that's relevant. I can see all the pieces. If we are given a maze or a map that we're trying to, for example, find the shortest path from one point to another, then I give you the whole map. There's no fog of war, there's no hidden parts or hidden information. So for this course, we'll be looking at fully observable states, and no history is required. So I can just look at the current state and make the best move. So believe it or not, this was not intuitive to me at first. If you're playing a game like chess, you don't need to know what happened in the past. You can just look at the current state of the board. Like you can walk into a game that's already half over and decide on the optimal move just given that. You don't need to know anything that's happened in the past. And there are a lot of problems that are like that, and there are a lot of problems that are not like that. And the agent's behavior is given by the agent function that maps a given percept sequence to an action. And that's just a fancy way of saying, like, given what I've seen so far, I think I should take this action. And if you think of your brain as a function that takes inputs and some time limit and produces outputs, this is exactly what's going on, right? Like, you're seeing me standing in front of here. You've decided, oh, this is boring, I'm going to look at my phone, right? So depending on your agent function and what you find to be interesting or whatever goal you're trying to achieve, you're going to take an action based on what you've seen so far. So here's an example. This is a picture of a person in midair, what looks to be the ocean and what looks to be a cliff. So let's say I'm trying to, I don't know, I'm really mean and I have like a paintball gun, right? And I'm trying to hit that person. So can I determine where to aim based on that picture alone? Right? So where should I probably aim? Below where they are. Why is that?
Because they're falling at the same time.
Okay, so based on your previous knowledge of the world, it's probably the case that this person started up here and is now here, right? But do we really know that? Maybe there's a trampoline down here that we can't see, and they're in the middle of a flip, right? So this problem would require like a history of what has happened over time in order to be able to make the best decision. We can't just look at that person in that instantaneous moment and decide where they're going to be 1 second from now, because we don't have all the information. Now, it just so happens that our laws of physics are such that if we did have about a second of information, we'd be able to determine that, right? But in general, for most problems, we do need this entire history. But for chess, we don't need that. The only exception for a game like chess is that there's a rule where, like, if the same move is repeated a bunch of times, then it's a draw. So the only other thing we would need right here is like the count of how many moves have been repeated and possibly a clock if we're playing a timed game of chess. But you can look at a game of chess and know, no matter what has happened in the past, no matter what order those moves were done in, I can take the optimal move right here. Here's an example from League of Legends. Anyone played League of Legends? Hopefully a couple of people. All right, you don't really need to know the game, but this objective here in the game is called the Baron, and it's a very strong monster that takes like a minute or so to kill depending on your level, and if you are the team that does the last hit point of damage to that monster, then you get all the benefits. You get all the gold, you get the buff, it like puts you way ahead in the game. So here what happened is that this is really old, this is like years old, but I just keep it in there. So this team down here in blue is currently killing the Baron, and this person up here comes in and times their shot at the exact instant to deal the last hit point of damage. Now if anyone in here plays League of Legends, they'll just blame the jungler on this, right? But this took a lot of skill from this player, but you're also just saying, oh look, they just walked in and just shot it as that thing was going down. Why is that so hard? The reason it's so hard is because here's the point of view from this player. They couldn't see what was happening, right? But that player, having all of their game knowledge, looked at a sequence of events, said, okay, the 5 of them are in there. I kind of know what items and damage per second that they can deal. So I think in about 15 seconds is when I should fire this bullet to try and steal the thing. Now this is really rare. It's a completely like cherry-picked example. But this is an example where you can't just look at a black screen and take the correct action. You would have to have known a bunch of stuff that happened all the way up to this in order to take that. So it's a pretty good example, especially when you get games with hidden information, right? Like playing poker, I don't know the cards in their hand, something like that. Okay, so an action taken by an agent, now we're going to get into like actual definitions that we can implement. An action taken by an agent in a given state transitions that state into another state. And so for the real world and for video games, the states are going by really quickly. Like 60 plus frames per second in a typical video game, and depending on whether or not you believe the universe is actually finite, some really large amount of times per second for an actual like physical example. But, so in this class, we're going to be dealing with, game states that transition at a reasonable pace, right? Not necessarily this quickly. And so what we have is we can view this as a sort of state machine. So hopefully you've all seen a finite state machine before at some point in a class. There are multiple different ways of representing this state machine, but here's a simple example. So let's say that we have two states in our environment, really simple environment. I'm at state 1 or I'm at state 2. So if I'm at state 1 and I choose action 0, I'm going to move to state 2. Similarly, if I'm at state 2 and I choose action 0, I go to state 1. So action 0 is basically switch states, and action 1 is stay at the same state. If I take this diagram and I represent it as a table, then I have states over here as the rows and actions as the column. And so going from state 1, taking action 1, then I stay at state 1. Similarly, you get the idea. I don't have to list them all out. But this is one way of representing an environment and the transitions through that environment. And if you think about it, a video game kind of does have something like that. You don't program the entire state machine. You don't list it as a big diagram. But you do have rules that transition you from one state to the next state based on the physics of the game, etc. So this is called the state transition function, STF. I'm just putting it down here so I can list it here a little bit more succinctly. And so it's the successor function, the state transition function can be represented either by a graph, like I just showed, by a table. A graph or a table is really only if the problems are small enough, but in general, it's a function, like a general function that takes in a state and an action and then produces the next state. And that could be as simple as something like this, or it could be as complex as a video game, which has a bunch of rules, or even like a real-world simulation. So if we have a state S and an action A, and we're going to stick with that terminology for the rest of the course, then S prime, that terminology means the next state of our environment. The next state of our environment is defined by applying the state transition function to S with action A. Okay, so I take a state, I do an action, I run it through the function, and I get the next state. That's what that means. So an example of an action, this is connect 4. We'll be doing connect 4 for assignment 3. And what you do in connect 4 is you choose a column and you drop a piece, and it goes down to the bottom of that column. So for assignment 3, an action, this is the current state, so you've got yellow pieces and red pieces. And then I'm going to choose my action as putting a piece in this column, and here's what I end up with. So this is S, this is A, this is S prime. Similarly, taking an action in a game of chess, I've got my current state S, my action is going to be knight to B2, and I'm going to have a new state where that knight has moved to that piece. You may have, a more complex action in a video game. So this is, I believe, Street Fighter 6 probably, where you have, when you get the game, you have all the different actions, and then you do actions that transitions you through states, and they might look like continuous states, but they're actually in the video game, right? It's a sequence of discrete states that you're actually stepping through. So it's very close to what we're doing here. And then you get professional StarCraft players who have 400 or 500 actions per minute while they're playing. It's just insane if you've actually watched them play the game. Of course, I can take actions in the real world as well. You can have robots that have actions like, okay, pick up the thing, put it in the other thing. Lots of different types of actions that we can take. Next, we're talking about policies. So a policy is a mapping from states to actions. So a policy is represented by, that's supposed to be the pi symbol, but PowerPoint's font isn't great for the pi symbol. And if we ever see a star in front of pi, that means it's the optimal policy. So the optimal policy means that it does the best thing, right? So if you had a literal perfect chess player, that chess player would have the optimal policy for playing chess. And so this policy is a function. So if I look up a current, or I pass a state into my policy, it returns an action. So a policy maps from states to actions, meaning that the policy could be, again, It could be a lookup table, an if statement, some arbitrary function calculation. It could be a neural network. It's a function in some respect, and it basically tells me what to do at action S. How did I get that policy? Well, throughout the course, we're going to figure out a bunch of different ways to arrive at a policy. But the policy is the thing that tells us what to do. Just like if you have a policy at work, you might have a dress policy or a customer policy or something like that. It just says, if you're in this situation, do this thing. So given we are in state S, do action A. So here's an example of one way to look at a policy, and this will be assignment 5 in the class, unless I end up changing it, which I might to something more interesting. But this grid, let's say that you are this agent, red circle, and you are trying to get to the closest green square. Okay, it doesn't matter which one, you just want to get to the closest one. What this grid represents are there are a bunch of arrows pointing in the direction that will lead you to the closest green square, right? And wherever there's multiple arrows, it just means you can take either one of them. So for example, if we're right here, we could either go up or left to get to the nearest green square as fast as possible. So that's an example of a policy. It's a way of representing what to do at a particular state. So this agent is at that state. What should they do? Well, according to this policy, they should move to the right. Anyone ever played blackjack before? So this, you've probably seen something like this. This is a blackjack betting table. So in this, the game of blackjack, I'll actually go over the rules of blackjack later for one of the lectures. But essentially, you have some cards, and in the casino, there's a dealer. The dealer has some cards. And this policy says, if you have these cards, and the dealer has this card, then you should do this. So this is another way of representing a policy as a table. We could also have a policy as a flow chart, right? So here's this great way of getting through life. Do you have a problem? No? Then don't worry. Do you have a problem? Yes. Can you do something about it? No. Well, if you can't do anything about it, why would you worry, right? But if you can do something about it, then you just do that thing, so don't worry, right? How simple it all is. So here's a lot of, here's how like I wake up in the morning, average about 3 times hitting the snooze button. But this is just one way. It's essentially a bunch of if statements and states, right? So this could be viewed as a policy as well. So that's what a policy is. But in general, again, a policy is an arbitrary function. It could be very complex, could be very simple, could be a table, could be a flowchart, whatever, but it's a function in general. Next, we have a concept called rationality. So a rational agent is the one that does the optimal action for each possible state. And what makes an optimal action? It's the action that makes the agent the most successful. So this is kind of circular logic. What makes the agent most successful? Well, it turns out that part of a problem is that we have to define a performance measure for that agent, right? It measures how successful that it has been. So if I'm putting something into Google Maps, what might the performance measure in Google Maps be for that agent that decides where we should go? Time taken, yeah. So how do I get there the quickest? A similar thing might be shortest distance, maybe the least gas, right? So lots of different performance measures that we could have for the same type of problem. And so a rational agent, therefore, has an optimal policy. And it is optimal within its level of knowledge. Okay, so that's really important. A rational agent does what's best given what it knows, right? But for example, it doesn't know like the outcome of a dice roll or something like that. So there's different, I'll get into that in a little bit. Performance measure is the criteria for success of an agent. So a successful agent is going to maximize this performance measure. Or depending on how you've defined the performance measure, like distance, you may want to minimize the performance measure. This is also called an evaluation function sometimes. So if we want to evaluate an agent and how it's doing, we apply this evaluation function. We try and maximize the return of that evaluation function. So here's a typical scenario. We have an agent that's placed in an environment. The agent is going to perform a sequence of actions, maybe go up, then left, then up again. These actions cause the environment to go through a sequence of states, and if the sequence of states is desirable, the agent has performed well and the evaluation is higher, or depending on how we phrased it, lower, right? So either we're minimizing or maximizing. So for example here, in Flappy Bird, I don't know if anyone here has ever played it, very simple game. I'm sure there's lots of clones out of it now. And in Flappy Bird, your agent, you are the agent, but your character, this little bird, just moves to the right. Okay, that's all it does. It goes to the right and it falls. And you only have one button, and the button flaps its wings. So you're trying to keep it going up and down properly within the pipes. And the physics of the game are such that this is a little bit difficult, right? So you fall pretty fast, you go up pretty fast. And so the success, what do I call it? Performance measure here is just go as far to the right as you can, right? And a surprising amount of video games are just go to the right as far as you can. Here is another thing which we'll become intimately familiar with in the coming assignments, which is a pathfinding problem. And so the performance measure here is I want to get from this spot up here down to this spot down here, or vice versa, as quickly as possible. And so we're going to define some actions. We're going to define which actions are legal, what can you do, what can you not do, and then we'll have a cost associated with the path, probably something like distance, and then we'll attempt to minimize that cost. In this pole balancing problem that we saw earlier, the performance measure is how long did the pole stay upright. Pretty simple performance measure, and we're trying to maximize that. And for some games, the performance measure is going to be really simple, which is just win the game. That's all you've got to do, is win the game. And so for a game of chess, that's really what you're doing, is winning. Does anyone play chess pretty regularly here? So winning the game is like a 1 or a 0, right? But sometimes you can't tell who's going to win. So what's one thing that people sometimes do to give like an evaluation to the board in a game of chess?
You're talking about the evolution bar?
Sorry?
The evolution bar, like +1 or...
Yeah, so there's what they do, what people do in many scenarios is come up with, because, okay, go win the game is kind of hard, right? How do I know if I'm winning or losing? How do I know if I'm going in the right direction, right? So this is a hard problem. And so what some people will do sometimes is, and we'll call these heuristic evaluation functions in a future lecture, but basically, okay, if I've taken your pawn and you haven't taken mine, then I'm up 1 pawn. Or if I've taken your queen, then that's +9 points for me, or -9 points for you, or a rook is 5 points, or however many points, right? So in many games, in StarCraft, for example, oh, they've got this level of economy. I've got 35 workers, right, to your 12 workers. Maybe I'm ahead. And so sometimes the performance measure, even though it is really simple, have I won or have I lost, we'll have these sort of intermediate performance measures to try and guide us toward the real performance measure. Someone here have a question? I saw a hand. Okay. But that gets a little bit tricky, and we'll see why in a future lecture. So rationality, how to make the optimal decision, depends on 4 things, or at least 4 things. 1, depends on the performance measure that defines success. Obviously, you have to know what you're trying to maximize. It depends on the agent's prior knowledge of the environment. So how much do you know about this environment? The actions that the agent can perform, because I'm going to give you a set of legal actions, and you're going to choose which action you want to do. And, of course, the agent's percept sequence. So what has it seen up to and including the current state? That's rationality. There's this other thing, which is omniscience. And rationality is not omniscience. An omniscient agent would know the exact outcome of all actions. So the outcome of actions, sometimes it's deterministic, okay? Sometimes it's not like we know exactly 100% of the time. If I try and move forward, I'm pretty much always going to move forward. Unless, well, okay, I have fallen in my life, so maybe 99% of the time I'll move forward. But if we're talking about a game of chance, like being dealt cards in a game of poker, or rolling some dice, or whatever, an omniscient agent knows the outcome of actions as well, right? So if I told you, okay, I have an example of this. And it knows the entire state of the environment. So if we're playing something like StarCraft, it knows what units you have without even having to look at them. Yep.
So you mentioned, I think last class, that the game of checkers has been solved.
Yep.
That we know like the optimal policy for every single state of the board to win the game.
Yep.
Would an agent following that optimal policy be considered omniscient, or would they be considered rational and following a perfect policy?
I would say rational. It's just a special case where they know everything. Yeah. But you could consider like a board game. Let's say when I tried to jump your piece, I had a 50% chance of making it, right? So in a game like that, where I have a 50% chance of capturing you, you can still have a rational, optimal policy figured out that takes the randomness into account, but you don't know the outcome of an action, what it will be for sure, right? Just because you don't know what's going to happen doesn't mean you can't still figure out what the best thing to do will be, okay? So an example here, let's say I bet you $100 that a six-sided die will be between 1 and 5. So if I tell you, okay, if it's between 1 and 5, I owe you $100, but if it's exactly a 6, you owe me $100. Who here would not take that bet? Right? Okay, a couple people. Maybe you really want your $100. But like, you can tell that if you play that game a bunch, you could get unlucky once, but that's a pretty heavily sided bet for you, right? A rational agent would take that bet. But a rational agent taking that bet may lose. It doesn't mean it was the wrong decision. And was that bet rational? Yes. Why? Well, it's something that has to do with something called expected value, which we'll talk about in the future, right? But if we did this 1,000,000 times, or an infinite amount of times, would we be up money, right? That's what expected value is. And this makes me so upset in the real world sometimes, because when you like, heroes in like sporting events are like made or broken by the outcome of an event rather than the decision of an event, right? Someone goes for this like crazy Hail Mary throw that only works out 1% of the time, and statistically it's a terrible throw, but they catch it that one game and they're an absolute genius for the whole media for the next week, right? It makes all the highlight plays, but it was still dumb, right? Buying a lottery ticket was still dumb, even if you won, because expected value is you're going to lose, right? So this kind of upsets me. It's like, oh, what a genius, they bought a winning lottery ticket. Like, anyway, we'll talk about more of that in the future. Environments. So an environment that a task takes place in is essentially the description of a problem. In the next lecture, we'll talk really specifically about how to form a well-defined problem. A rational agent is then a solution to that problem. The specification and properties of an environment greatly impact the design of a rational agent to act within it. And remember that a state is a particular configuration of a given environment. So what I meant by this point right here is that certain environments have certain properties that make it so that certain algorithms are best and certain other algorithms are worst, or it may even be the case that you cannot apply this algorithm if it doesn't have a certain type of property. And so this may be an exam question once we learn some algorithms and the type of things, type of environments that it works on, what type of algorithm would you apply here? And that's a really good thing, because you want to know the theoretical properties of some of these algorithms so that you don't waste a bunch of time trying to implement the algorithm, and that'll take a long time. So, for example, an example environment is chess. That is an environment that we can have an agent act in. The agent will be the player. So in this environment, we have rules and boundaries, right? That's kind of like the physics of the chess environment. So over here we have an 8x8 board, checkerboard pattern with some white squares, some black squares. We have legal actions that can be taken in this environment. So, queens can move one way, pawns can move another way. We have a starting state of this environment. So at the start of a game of chess, all the pieces have to be arranged in a certain way. And we have a goal condition or a goal state that we are trying to get to. So when you talk about goals, a goal could be, hey, there is a particular state that we're trying to arrive to. So for example, if I'm trying to get to the engineering building, maybe the state of the environment that I want to be in is the state where I am in the engineering building. There's like a single state that I'm trying to get to. In something like chess, there's more of a goal condition than a single goal state, right? There are billions of possible goal states in chess. There's a lot of different ways to checkmate somebody or draw somebody in a game of chess. And that would be a goal condition. So you'd test for a bunch of things, right? Is the king in check? Can the king not move on the next turn? Things like this. So here, this would be the starting state of a game of chess. And this would be maybe a mid-game state of a game of chess that's already in play. And the agent can observe the entire environment in a game of chess. Okay, so all the pieces that are there, all the pieces that have been captured, you can infer that, and this is all you need to make the decision. So for the agent, the state of the environment is based on the observation that it can make. The observation may not be a complete representation of the environment state. Like, picture a game of chess where you just can't see the other player's pieces. And it's not until you try and move that the pieces are revealed, or something like that. And so the agent's observation, the state, is all that it can use to make a decision. That's all you can do, right? Is whatever you can perceive, whatever information you've been given, that's all that you can base it on. So for example, there's problems like driving. Like if you are in the real world driving, you've got a lot of knowledge, you've learned a bunch of stuff about driving, but you can't see what's around that corner, right? If you could see the drunk driver coming really fast, you'd probably slow down in advance, right? But you can't slow down in advance all the time just in case there might be someone there who's not driving safely, right? So there are all these things in the real world that you cannot see that may affect your actions. And so if you're doing something like self-driving cars, for example, here, this is what the agent can perceive. So, okay, there are some, in this particular example, with these particular sensors, maybe you can see this much of the road in front of it. It's got some laser range finding, so we can say, okay, there's a car 10 feet to the left of me of whatever, but it cannot see everything. Okay, that's the important part. I wonder what that noise is. Okay, so now comes in, now that we can identify different states, we have this concept of state and action spaces. So the state space, it's not a physical space, it's a numerical space, and the state space is the number of possible configurations of the environment for a given problem. Okay? So how many possible chess configurations are there? If we're playing tic-tac-toe, how many possible ways can I arrange a tic-tac-toe board? How many possible ways can I put a bunch of cars on the road, right? And similarly, the action space of an environment is the number of possible actions that we can take from a state. And because the number of actions that we can take from a state varies sometimes, right? Like, think about the very beginning of a chess game. You can only move your pawns or your rooks, right? You can't move everything. Versus like halfway through the game, you can make like 50 or 60 different moves. And so sometimes the action space is going to be given as like an average case or a worst case or something like that. And what this does is it's used as an estimation of the complexity of a problem. And you've all done some sort of algorithmic complexity course, right? This, I'm not talking about like what's the big O of chess, but it's kind of similar to that, right? We're trying to count the number of things. And this is an estimation of complexity. And what that means is if an environment or a problem has like 10,000 or less possible states, then it's very easy for you to make the best decision because you would just simulate all 10,000 of them because you have a computer and choose the best one. But if it has a lot, then you don't know whether or not the problem is going to be hard because you can't enumerate it. So what do I mean by that? Well, let's look at tic-tac-toe. This is the state space complexity of tic-tac-toe. Well, I've got X's, O's, or blanks, and I've got 9 possible spaces. So for each of my 9 possible spaces, I have 3 choices. And so the calculation of the state space of tic-tac-toe is 3 to the power of 9, which is approximately 10 to the power of 4. Now, of course, you may say so 4, if we're talking about like exponential, like 10 to the power of 4, 4 would be the state space complexity of tic-tac-toe. But, as many of you know, some of those positions, like if you rotate the board 90 degrees, 180 degrees, 270 degrees, it's still essentially the same state of tic-tac-toe, or if you flip it, right? So even though, yes, 3 to the power of 9 is 19,863, the number of distinct possible ways to order that is much, much lower, like several hundred to 1,000, okay? Next, let's look at chess. We're going to bump up in complexity a bit. So what we've done here is, okay, there's 20,000 possible states of tic-tac-toe. We can trivially write a program to enumerate all of those and solve tic-tac-toe. Anyone here can trivially solve tic-tac-toe. So if someone came to you at a job and said, hey, we need an AI to solve tic-tac-toe, first thing you do, calculate the state space. Can I enumerate it? Yes. Okay, I can make the perfect move in tic-tac-toe. Done. No need for any fancy algorithm. Next, they come to you and say, make an AI for chess. Okay, 64 pieces on the board. Here's the number of combinations of empty board spaces with different types of pieces. I'm not going to go into all the details of this calculation, but it's essentially 10 to the power of 42. Okay, 10 to the power of 43, which is an insane number of possible, so that's what? 1,000 is about 10 to the 10, 1,000 times 1,000 times 1,000 times 1,000 times 8. So lots and lots of pieces. Let's look at the board game of Go. Similar to tic-tac-toe, there's 3 possible things for every board piece, a black or a white or a blank. It's 19 by 19, and so 3 to the power of 361, okay? Which is insane because, and if I look at this, so 10,000 for tic-tac-toe, 10 tredecillion, whatever that is, for chess, and 10 sexquinque, it's not even a word at this point, right? So the number of atoms in the universe is around 10 to the power of 80. So if you take 80 away from this, you've got 90 left. So if every atom in the universe could perform 10 to the 90 calculations per second, then you'd be able to solve this in a second, right? But the number of seconds in the universe that has been like in the 14 billion years or whatever, like it's impossible. So you can look at this and say, okay, the number is so big, I am not going to try and enumerate the whole game because it's impossible. Now that doesn't mean that the problem is complex. It just means that it's not trivially solvable. It turns out that Go is pretty complex, but okay. This is the state space complexity. That's the number of different possible configurations of the board that there are. In a lecture or two, we're going to talk about game trees. Game tree complexity is essentially the number of possible ways that you can play the game to the end, right? So there's many different ways to arrive at each of these possible states. I could have gone left first instead of right, but I arrive at the same state. So the game tree complexity, which is how I would search through different actions, we'll get into that, is even bigger than that. So we can't search over all possible actions for every state either. So let's have a look at this. Seconds in a century, 10 to the power of 9. Number of total humans born, 11. Age of the universe, okay, I had that here in seconds, is only 17. The diameter of the universe in meters, the number of stars in the universe, the number of atoms in the universe, the number of protons needed to fill the universe. The protons are pretty small. And here's the Go, right? It may as well be infinite at that point. So it's pretty complex. StarCraft, is insanely bigger than Go if you actually wanted to solve the game, and like a lower bound of like 10 to the 1,000 to the 1,000. Like it's crazy how many different possible states of video games that there are. So just keep in mind that a large state space does not prove that it's complex. It just proves that it can't be solved in a trivial way. So consider the game of Go. So Go has some complicated mechanics, like I'm going to place pieces on the board, and if I surround your pieces, I get to capture them. And then at the end of the game of Go, the person with the most pieces left is the winner, and it's over when you can no longer place pieces. Consider the game of Go if you can't capture. Then what happens? Well, I place a piece, you place a piece, I place a piece, you place a piece. 361 times. That's an odd number. We can never capture anything. So whoever went first is going to go last and just have one more piece. So you know you've solved this game of Go. Even though this version of the game still has the same state and action complexity of the original version of Go, you can work out in your head that this game is trivially solvable. And it doesn't matter what action you take, because you'll always lose. So it doesn't mean that it is complex, it just means that it can be complex. So it shows us that the computational complexity required to solve the game via exhaustive search, meaning searching everything that could possibly happen, is it's easy. All right, environment definition. How you define an environment matters. It gives you the rules and dynamics that govern the environment, the physics, the game rules, etc. The legal actions allowed at any state of the game, the initial states and the goal states, and that is usually given by the problem instance. So you can have an environment definition, right? Let's say I'm trying to pathfind, again, from here to the engineering building. That is, the environment might be the campus, my legal actions might be where I can walk, but another instance of the problem might be trying to get from the library to the UC, or from the math building to the arts building, right? So you can have one environment that has many different problem instances. And environments have many different properties as well. So the rest of the lecture is going to be explaining what these properties are. The first property, and these are in no particular order, they're just in kind of importance, but kind of not. But either way, you should know them all for the exam. So the first property is whether the environment is fully observable, like chess, or partially observable, like StarCraft. So fully observable, the agent's sensors give it access to the complete state of the environment at any given time, or at least access to the relevant part of the states to take the actions that are needed. And in games, these are called perfect information games. So if a game is perfect information, you know that you have access to the full state. Partially observable, there is some data that is hidden or occluded. The sensors may be noisy if you have a robot, for example, or you might be playing a game where one player has access to some information that another player doesn't. So if we're playing poker, I can see my cards, but you can't see my cards, right? So that's an imperfect information game. So here we have chess versus StarCraft. In StarCraft, like, you have a fog of war, you can't see my units until you come up to my units. Deterministic versus stochastic. Deterministic essentially means no randomness, right? So the next state of the environment is entirely determined by the current state and the action of the agent, and there is no randomness in the environment. Versus a stochastic environment, there may be some uncertainty about the results of actions. So a random chance, like a dice roll, a card draw, etc., and there is some random nature to the environment. And think of this from the point of view of the agent. Okay? Does the agent know what's going to happen, or is there some chance that something could happen? And I remember playing League of Legends years ago when you could choose runes, starting runes, and everybody would take one rune that gave you like a 1% chance to crit. And like, there was an annoying amount of if you crit, you do double damage, but it's a 1% chance. But sometimes in the very early game, that one crit would like kill somebody and you'd get a huge advantage. And it was really annoying. So like critical strike chance and stuff in video games, that is all randomness, right? So But another form of randomness is the deal of some cards or the roll of some dice, right? It's not all video games here. So again, chess is sort of the standard deterministic. There's no randomness in chess. I have played a random version of chess before, which you just say, okay, there's a 50% chance that the piece will be taken or not taken. And it's a really interesting game because you could just like mess up your move. So do you try a move, which gives you a 50% chance of taking it? If it fails, like if the die roll fails, then you just move your piece back and you've wasted your turn. Or do you move somewhere that gains position with 100% certainty? It's a kind of interesting game. Next is episodic versus sequential. Episodic means that the agent's experience and actions are divided into atomic episodes, and the agent perceives the current state and takes an action, and the next episode does not depend on any previous decisions that you've made. Sequential, which is most interesting problems, the current action can influence future decisions, and actions may have long-term consequences. So, an episodic task might be something like optical character recognition. Like, whether or not I think this character is a 3 has no bearing on what I think the next character is, right? I'm not, unless like, okay, if you're actively learning during the task, it might. But in general, this is an episodic task. You see one thing, you make a decision, it has no bearing on the next thing that you're going to do. Versus in chess, the second state of the game depends on your action at the first state of the game, and so on and so forth, right? So where you move your first piece is going to matter hugely down the road. Then there's dynamic versus static. So a dynamic environment, the environment is going to change while the agent is making a decision. And it's continuously asking the agent what to do, right? So, for example, the real world is a dynamic environment. If I throw my water bottle at your face, you've got to make a decision where to move before the water bottle gets there. I don't want to get fired, so I'm not going to do that. But that's an example of a dynamic, that's what we call dynamic or real-time environment. In a static environment, the environment only changes when you take an action. Right? So decision-making time doesn't matter. So if you're, again, looking in games, this would be like real-time games, like most video games, versus turn-based games like something like Civilization or chess or checkers or whatever. So again, video games versus board games, basically. Can you imagine a real-time version, like a dynamic version of chess? Like, it's as fast as you can move the pieces? That'd be pretty funny. The next property is discrete versus continuous. And the distinction is applied to the state of the environment, and it basically determines the way that time and sometimes distance is handled in the environment. So in a discrete environment, there are a finite number of distinct states, and there are a discrete set of percepts and actions. In a continuous environment, there is a continuous time and continuous action space, right? So in a real world, I can decide at an arbitrary angle where to move, but in a video game or on a board game, maybe I only can move up, down, left, or right. So again, an example here, these would be discrete spaces. So you have to play one card or be dealt one card or bet a certain amount of money in a game of poker. Or in chess, you're moving a discrete piece across the board. A continuous environment, like self-driving cars, all that stuff is happening very quickly. You can move any amount that you want in that environment. Now, oftentimes, the way that that's actually done is to take a continuous environment, like the real world, and then chop it up into discrete parts so that we can apply our algorithms to it. Because we still don't have truly continuous numerical representations in a computational space, right? Even floating point numbers, even though they look kind of continuous, are actually discrete. Next, there's single agent versus multi-agent. I know there's a lot of properties. Don't worry about it. Single agent, only one agent is there at a time. So you might have something like solving a Sudoku puzzle. Okay? So that would be an example of a single agent problem. Or if you're in a maze and you're trying to get out of the maze and you're the only one there, now there's a path, that pathfinding problem is a single agent problem. Or a multi-agent problem, you could have multiple agents acting together, not necessarily at the same time, but just in the same environment, and they may be cooperative or competitive. So here, for example, you have a single agent problem of one agent trying to find the quickest path from a start to a goal, but over here you have a multi-agent problem. So your actions are affecting other agents' actions in that game. Chess is also a multi-agent problem. Where I move my pieces determines the legality of where you can move your pieces. Next is complete versus incomplete information. So before there was perfect versus imperfect information, where that meant how much of the state you can see. Complete versus incomplete information is a little bit different. Complete information, all the game rules and the physics of the environment are known, and all the possible actions are known. However, in an incomplete information environment, which actually doesn't happen super often, the game rules or the physics may not be known, right? You might think of a robotic problem like clean the floor, but it didn't tell me what I can do. It's just like applying voltages to the arms and trying to figure out what to do, which can be done with something like reinforcement learning. The actions may have to be discovered. So we're not going to be dealing with any incomplete information in this class. Has anyone ever played the card game called Mao? Yeah, so it's a card game where like multiple people can play, but the point of the game is that nobody knows the rules. And so like one person is kind of the headmaster of the game, and they can like discipline people for not knowing the rules. But if you join the game, you have to figure out the rules. Right, so like one rule might be, oh, if a jack is played, you have to touch your finger with your nose, and you just see people doing stuff and figure out the rules as you go. It's like the weirdest drinking game ever, but it can be fun. So here's a table of all of those things in order, and you can kind of see as one of those options was always the easiest, and one of those options was always the hardest. Right? If you have full information, that's an easier problem than not having full information. If you know all the rules, that's easier than having all the rules. If there's no randomness, that's easier than having randomness in terms of how you would go about solving the problem. So if we start up here with something like a crossword puzzle or a Sudoku, that is a sequential problem. It is single agent, deterministic, fully observable, static, and discrete. Next, let's say, okay, I want to add another agent. So I'm going to make it multi-agent. Well, chess is one of those problems. So it's sequential, multi-agent, deterministic, fully observable, static, and discrete. If I take those properties and add some randomness, now I've got a game like backgammon. Right? So backgammon has some dice rolling. Based on the outcome of the dice, you move your pieces. And the problem there is that it's hard to plan for the future because you don't know what you're going to roll in the future. Right? So you've got to do these like averages and stuff and have interesting strategies. But in backgammon, the full game is still fully observable. So let's make a new game where now we can't see the whole state of the game. Well, poker is multi-agent, stochastic, and partially observable because I can't see the cards of my opponents. But it's still static and discrete. Okay, now let's make it dynamic. Right? So things are happening even if you're not taking actions. Right? Like if you're killing my base in StarCraft and I'm just sitting there, it's still going to happen, right? So that's dynamic. At least in poker, your opponents aren't doing anything while you're taking your turn to act. And then if we go one step up to the real world or something like robotics, now we also have a continuous space that we're working in. So on an exam, something that I might ask you is give me an example of an environment that is multi-agent, stochastic, fully observable, dynamic, blah, 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 right? Or I can give one of the examples that we've said here, like, okay, I'll give you backgammon, right? And you have to tell me the properties. And I'll tell you exactly, you don't have to remember the names of all these properties, but I will ask you very specifically, hey, here's this game. I like going in the opposite direction where I give you the properties and you tell me an environment, because I might say the name of a game that you've never really played before, right? And that's not really fair. And so that's it for this lecture. Definitely finishing in time today. I thought I had something to say, but I don't. So that's it.